Hello, welcome to another module in this massive open online course on principles of CDMA, MIMO, OFDM wireless communication systems. So, in the last lecture we had seen that basically diversity, for instance having multiple receive antennas at the receiver, can improve the performance of the wireless communication system by reducing the bit error rate. We term this as diversity, and specifically having multiple antennas is termed as receive diversity, right, as you can see in this figure over here. So, now let us start our analysis of a multiple antenna system. So, what we want to start analyzing today is a multiple antenna system. And what I would like to consider, I would like to consider a transmitter as we had seen before and a receiver. So, I have a transmitter, I have a receiver, and let us say I have a single antenna at the transmitter, but I have two antennas at the receiver. I am calling this transmit antenna 1, receive antenna 1, receive antenna 2. Let the fading coefficient between the transmit antenna 1 and receive antenna 1 be denoted by H1. The fading coefficient between transmit antenna 1 and receive antenna 2 is denoted by H2. So, H1 equals, H1 is the fading coefficient between T1 comma R1, transmit antenna 1, receive antenna 1. H2 is the fading coefficient between T1 comma R2. Further, as usual, the transmitted symbol is X, that is X is the transmitted symbol. Received symbol on receive antenna 1 is Y1, on receive antenna 2 is Y2. So, Y1 equals the symbol received on R1, Y2 equals symbol received on R2, and therefore, we have a system with a single transmit antenna, two receive antennas, and X is the transmitted symbol, Y1 is the received symbol on R1 which is receive antenna 1, Y2 is the received symbol on R2 which is receive antenna 2, and H1 is the channel coefficient between transmit antenna, that is T1, and R1 receive antenna 1, H2 is the channel coefficient between T1 and R2. And now, we would like to develop a model for this system, and therefore, I can model this system as, so the system can be modeled as Y1 equals H1x plus N1, Y2 equals H2x plus N2, where N1 and N2. So, N1 is the noise at receive antenna 1, noise at R1, N2 is noise at R2, receive antenna 2. And so, what we have done is we have developed a simple model based on the previous model for the fading wireless channel. We have extended this model to a wireless channel with multiple receive antennas. So, what we are saying is we have single transmit antenna from which we are transmitting symbol x, but we have two receive antennas on which we are receiving symbols y1 and y2 respectively. and the corresponding noise components are N1 and N2. Further, similar to before, we are going to assume that both these N1 comma N2 are Gaussian in nature, and these are noise power, each has 0 mean, both of these are 0 mean. Further, each has power or variance sigma square. That is, if I look at expected value of magnitude N1 square equals expected value of magnitude N2 square equals sigma square. That is, each of these noise components has power sigma square. Further, we are going to assume another important property. We are going to assume that these two noise components at the different antennas are independent, or basically in the case of a Gaussian, these are uncorrelated. That is, we are going to assume that expected value of N1, N2, N1 times N2 equals 0, which basically implies that these noise components N1 comma N2 are uncorrelated, and further, since they are Gaussian, for the case of Gaussian, uncorrelated means independent. So, we are assuming these noise components N1 and N2 are basically uncorrelated, that is, expected value of N1 times N2 equals 0. Further, just to simplify our derivation, our life a little bit initially, what we are going to assume is that we are going to assume that this system, everything is real, that is, the channel coefficients H1 and H2 are real, although these channel coefficients in reality, in practice, these are Rayleigh faded channel coefficients. These are contain the in phase and quadrature components, as we had seen before, that is x plus jy. But temporarily for this part, we are going to assume that these H1 and H2, these channel coefficients H1 and H2 are real quantities. That simplifies our derivation initially. So, what we have is we have y1 equals h1x plus n1, y2 equals h2x plus n2, where the noise components n1, n2 at the different antennas are Gaussian in nature, have 0 mean, identical variance sigma square, and they are also uncorrelated. And therefore, now I can represent this system as follows. I can write this system as a vector y1, y2 equals h1, h2 times x plus, this is a vector model for this communication system. Now, if you look at this, this is the received vector which can be denoted by y bar. This is the channel vector which consists of fading coefficients h1 comma h2. So, this can be denoted by h bar, and this is the noise vector which can be denoted by n bar. Therefore, I can represent this system as y bar equals h bar x plus n bar. This is the vector model for this communication system, with two receive antennas, right. So, at the receiver we have two receive antennas, and what we have done is we have developed a vector model for this communication system with two receive antennas. And now we have to process these received signals at the receiver. So, we have to process the signals at the receiver. What we are going to do is basically I have two received symbols. So, we have two received symbols these are y1 comma y2. At the receiver we are going to combine them. So, we are going to combine these two symbols. and we are going to combine these symbols as follows. We are going to form a new symbol y tilde as a weighted combination of these two symbols, that is W1 y1 plus W2 y2. So, these W1 W2, these are our combining weights, these W1 W2, these are the combining weights, and I can therefore combine them as W1 y1 plus W2 y2, that is I am performing a weighted combination, which can also be expressed as the row vector W1 W2 times the column vector y1 y2, which is nothing but W bar transpose times y bar, where y bar, as we have already seen, is the vector y1 comma y2, and W bar is the vector W1 comma W2. So, now we have written this combining at the receiver as W bar transpose times y bar, which gives us W1 y1 plus W2 y2, where W bar is the column vector W1 W2, and y bar is the vector y1 comma y1 y2, right, that is the received vector. Okay. And now, as we have seen previously, we have y bar equals h bar x plus n bar. So, I can substitute this in our system model here. So, I have y tilde equals W bar transpose y bar, but y bar equals h bar x plus n bar. So, this is W bar transpose h bar x plus n bar, which is W bar transpose h bar times x plus W bar transpose n bar. And now, you can clearly see this W bar transpose h x bar is the signal component, W bar transpose n bar is this is the noise component. So, we have for this signal, we have the signal component and the noise component, and therefore, the SNR for this, the signal to noise power ratio, is the power of the signal component, that is magnitude of W bar transpose h bar whole square times p divided by the noise component, that is the expected value of magnitude of W bar transpose n bar whole square. So, we have the signal to noise power ratio, which is the power of the signal component, but the signal component is W bar transpose h bar, magnitude square of that times the power of the transmitted signal, that is x, which is p. So, we have received signal power is magnitude of W bar transpose h bar square times p divided by the noise power. The noise is W bar transpose n bar, therefore, the noise power is the expected value of W bar transpose n bar whole square. Now, let us look at the noise power. Let us try to calculate the noise power. Consider the noise. Now, when I consider the noise, I have the noise equals W bar transpose n bar, which is W1 W2 times N1 N2, which is basically W1 N1 plus W2 N2. And therefore, if I now look at the noise power, that is the expected value of W1 N1 plus W2 N2 whole square, which is equal to expected value of W1 square N1 square plus W2 square N2 square plus twice W1 W2 N1 N2. And now, if I take the expected value of this, this is W1 square expected value of N1 square plus W2 square expected value of N2 square plus twice W1 W2 expected value of N1 N2. And now, we have seen expected value of N1 square, this is noise power which is sigma square, expected value of N2 square is again noise power which is sigma square, and expected value of N1 N2 this is 0. We had seen from our earlier discussion expected value of N1 N2 is 0, because we have assumed that these noise components N1 and N2 at two different antennas to be uncorrelated. Therefore, now we have noise power which can be simplified as W1 square sigma square plus W2 square sigma square. So, we have our noise power which is expected value of magnitude of W bar transpose N bar whole square. This is our noise power. The noise power is equal to W1 square sigma square plus W2 square sigma square, which is equal to sigma square W1 square plus W2 square, which is equal to sigma square times the norm of our vector W bar. This is norm of the vector W bar square, because remember our vector W bar is equal to W1 comma W2. Therefore, norm W bar square vector norm square equals W1 square plus W2 square. So, I have the noise power equals sigma square W bar square, and therefore, my SNR, now I can substitute this in my expression for SNR. So, my SNR equals norm of W bar transpose H bar square P divided by sigma square norm W bar square. In fact, I am going to write this again. My SNR therefore, can be derived as SNR can be obtained as SNR in this system with two receive antennas is P times W bar transpose H bar square divided by sigma square norm W bar square, and therefore, this is the expression for my SNR, that is P, which is the transmitted power, times W bar magnitude of W bar transpose H bar whole square divided by sigma square times norm W bar square. Now, if you look at this quantity W bar transpose H bar, let us look at this quantity W bar transpose H bar, this is W1 W2 times H1 H2, which is equal to W1 H1 plus W2 H2, which you can clearly see is basically from your knowledge of high school vector calculus, this is W bar dot product of H bar. So, from your high school vector calculus knowledge, from vector calculus this is the dot product between W bar H bar, that is if I have two vectors, my vector W bar and my vector H bar, this is the dot product between W bar H bar, and therefore, magnitude W bar H bar equals norm of W bar times norm of H bar times cosine of theta, where theta is the angle between W bar and H bar. So, magnitude of W bar transpose H bar
equals norm W bar times norm of H bar times cosine theta, where theta is the angle between W bar and H bar. This is the property, this is the definition of the dot product. Therefore, if I look at W bar dot H bar whole square, that is equal to norm of W bar square times norm of H bar square times cosine square of theta. And now what I can do, I can substitute this in our expression for SNR. Therefore, our SNR equals P times norm of W bar square times norm of H bar square cosine square theta divided by sigma square times norm of W bar square. This norm of W bar square in the numerator and denominator cancels. So, I have P divided by sigma square times norm of H bar square times cosine square theta, and this is maximum. You can see this is maximum when cosine square theta is maximum, but we know that the maximum value of cosine theta or cosine square theta is 1, and that occurs when theta is equal to 0. So, the maximum value of cosine square theta, the maximum value of cosine square theta maximum value of cosine square theta is 1 occurs when theta equals 0. That means, if you look at this, what we are saying is the angle theta between W bar and H bar, that has to be 0 for the SNR to be maximized. Therefore, what we are saying is W bar has to point along the direction of the channel vector H bar. So, what we are saying is for SNR to be maximized, our W bar and H bar. So, let us say this is my H bar, this is my W bar. The W bar and H bar have to be along pointing in the same direction, that is W bar has to be proportional to H bar. For SNR to be maximized, W bar has to be along the direction of H bar, or vector W bar has to be proportional to H bar. Therefore, for SNR to be maximized, theta equals 0 degrees implies W bar has to be along the direction of H bar, or W bar, other way of saying that is W bar is proportional to the vector H bar. The vector W bar is proportional to H bar. And in that scenario, what we have is, if cosine square theta is equal to 1, in that scenario what we have is SNR equals P times norm H bar square divided by sigma square, which is equal to P times magnitude H1 square plus magnitude H2 square divided by sigma square. And now, how can we set W bar? We said W bar has to be proportional to H bar. One can choose W bar such that the norm of the vector W bar is unity, which means I can choose W bar to be H bar divided by the norm of H bar. So, I can choose W bar such that W bar equals 1 over norm of H bar times H1 H2, which is equal to basically 1 over square root of magnitude H1 square plus magnitude H2 square times H1 H times the vector h1 h2, and the same vector w bar can be used for, now we are going to relax the assumption that the channel coefficients are real. The same vector w bar, that is w bar equals h bar divided by norm h bar, can be used for complex channel coefficients h1 comma h2, except instead of doing w bar transpose h bar, we have to do w bar Hermitian h bar. So, for complex coefficients, use w bar Hermitian y bar at the receiver. That is, if we have w bar equals w1 w2, at the receiver perform combining as w bar Hermitian y bar, that is, this is the combining at the receiver, which is equal to w1. Now, you have to take conjugates, because you are taking Hermitian w1 conjugate, w2 conjugate, y1, y2, which is equal to w1 conjugate y1 plus w2 conjugate w1 conjugate y1 plus w2 conjugate y2. That is going to be the only difference when you have complex channel coefficients and therefore complex received signals y1 and y2. And the vector, the optimal beam for the vector, the combining weight vector, the optimal combining weight vector w bar is still given as h bar divided by norm of h bar, which is equal to 1 over square root of magnitude h1 square plus magnitude h2 square times h1 comma h2. And since this maximizes, this vector defined in this fashion maximizes the SNR, the ratio of the SNR, the ratio of the signal power to the noise power, this is also known as the maximal ratio combiner. This vector w bar, which is h bar divided by norm h, which maximizes the SNR at the receiver, is also termed as the maximal ratio combiner. So, this is also termed as the maximal or simply abbreviated as MRC. The maximal ratio combiner, which is abbreviated as the MRC, maximizes the SNR at the receiver in a multiple receive antenna system, and employing the maximal ratio combining, one can therefore maximize the performance of the system, and we are also going to see later how this leads to a reduction of the bit rate in a wireless communication system. So, in this module what we have seen is, we have seen a very important concept, that is, if we have multiple antennas at the receiver, that is receive diversity, when I have two receive antennas, what are the properties of the noise, that is, we have assumed the noise elements at the two antennas to be of equal power and uncorrelated, and in such scenario what is the optimal, how to optimally combine the signals received at the two receive antennas y1 and y2. We have proved and we have rigorously demonstrated that one has to use the maximal ratio combiner, that is the vector h bar, vector w bar is equal to h bar divided by norm h, and performing the optimal combining as w bar Hermitian y bar at the receiver maximizes the signal to noise power ratio at the receiver. All right. So, this is an important concept. We are going to stop here and then continue with this concept, explore this concept further in the subsequent modules. Thank you very much.